we kind of arrived last time. We said at the beginning of the course we were going to investigate and kind of develop from the ground up this idea of, you know how fast a quantity is changing at every moment, and you want to know how much of it you have at every moment. And we kind of got to the big punchline of that 4-day process, which was this. So let's talk about this slide. So we came up with some key functions, which was kind of the answer to this question, or our endeavor. And so we got these two kind of primary fundamental functions. So what do we call that first one? F of x equals f of a plus the integral from a to x r of ft dt. We call that's our exact total accumulation. This is how much of it we have at every moment. This is exactly what this is. F of x would be how much of a quantity we have at every moment. Quantity being temperature, height, volume, mass, any kind of real world quantity. Okay? What does this do? So what does it do? It gives us the total amount of the quantity in question at the current value of x. So it's a function. So for any, x could often is time, but it doesn't have to be time, a time variable. So at any given time, this function is telling you how much of the stuff we have, right? And then this one was our exact net accumulation. And so what did that tell us? So that was just almost exact total accumulation. It gave us how much f has varied starting from x equals a up to any current value of x. So it's net accumulation, meaning how much variation or how much change in the quantity's value since some starting point, a. Okay? And so the big question then is, if I want to write a total accumulation function or the net accumulation function, what do I need? What's the key thing that if I had this key thing, I'd just be able to write down what the exact total accumulation or exact net accumulation is? What is this thing that we need? Anybody? If I want to write the exact net accumulation of a function, what do I need to do that? The rate of change of that quantity. Yeah, this is a huge point. All I need is the rate of change, how fast the quantity is changing at every moment, right? You know how much the quantity is changing at every moment, and you want to know how much of it you have. So that means if we know the rate of change, we can write down either exact net accumulation or exact total accumulation. Okay? All right, so let's practice. So when you see a notation like this, so this is the integral from 3 to x of the square root of t dt. So now we want to think, oh, this is exact net accumulation. It's a function. So I want to imagine it's some net accumulation function for some quantity given by f, right? So some quantity given by the function f. Well, this will tell me this is the exact accumulation of changes in some quantity f due to the variable rate of change of square root of x, that's the rate of change, at every moment from t starting at 3 up to x. So it's giving us the exact net accumulation at this rate starting from 3 up to x. So when we see integrals, we want to think of them in terms of net accumulation. Here's another one. There's two more. And so the goal would be that you could write a statement out that explains what this notation means, and not just copy this word for word and change some of the things, right? So in your own words, could you come up with a statement that interprets what that is right there? Okay, again, we want to think of it as a net accumulation function, right? We want to think of that as a net accumulation function for some quantity f, and we say, oh, what's the rate of change of that quantity? Sine x. Sine x is the rate. Where are we starting accumulating from? Where are we going to start accumulating and start keeping track of the net variation? X equals negative 4.8. So this is the exact net change in a function f as u varies from negative 4.8 to x, if the rate of change of, that should say f right there, is the sine function. Okay, now what about this? So now this one actually is the integral from 6 to 12. Is this a function or a value? This whole expression here, is that a function or a value, that whole expression?
It's a value.
Okay, good, it's a value. So this is no longer a function. And so, but we still want to think of it as the value of a specific value of a net accumulation function. So we want to think of this like as, still think of it as a function, but now it's a particular value of the function, or a sub f of 12. Okay, does that make sense? So you saw lots of these in Calc 1, and we're going to see lots of them in Calc 2. And so I want you to have a new perspective on it, that this is, okay, this was from some net accumulation function. It's the particular value when an independent value x is equal to 12. Or in other words, it's the exact net variation of a quantity given by f, where the rate of change is x squared minus 7, as x varies from 6 to 12. So if you vary x from 6 to 12 and accumulate at this rate, you're going to get a number, you're going to get a value. Okay, is this making sense? So interpreting the meaning of integral expressions, super important. So we want to from now on, we want to do that in the light of our first week of the course, where we talked about, we built up this integral as a net accumulation, or variation since a starting point, right? Variation since a starting value of the independent variable. Okay, what's another way to write this amount? So what are we talking about? We're talking about the amount that the function f, the quantity given by f, varies as x varies from 6 to 12. What would be another kind of more simpler way to write that? If it's how much f has varied from 6 to 12, we can write that pretty simply, right? You guys practiced with function notation, right? The variation in a function as x varies from one value to another. How do we express that?
AF of 12 minus
Okay, that would be right, because AF of 6 is actually 0. AF of 6 is 0 because that'd be the from 6 to 6. But what about using function f? How much does function f change as x changes from 6 to 12? So we worked on this in recitation last week, and all this practice with function.
Minus 7, 12 squared minus 7 minus 6 squared minus 7.
Well, but this isn't the function f, right? You got the right idea, but this is the rate of change of f, not f. We want the change in f as x goes from 6 to 12.
Minus f of 6.
What's that?
F of 12 minus f of 6.
There we go. Hopefully lots of you were thinking this. This expression is the same as f of 12 minus f of 6, right? Isn't it how much the function f has changed starting from 6 to x equals 12? So this is expressing it just as like final minus initial value of the quantity. This is expressing it as what? The net accumulation of little changes at this rate, right? Starting from 6, ending at 12. We're going to add up these little changes, right? M dx. So it's just two different ways of expressing the exact same quantity. Adding up little changes expressed as rate times change in x, starting from 6 and ending at 12, or just the final value of the quantity at 12 minus the initial value of the quantity, which is at 6. Does that make sense?
I just have a question.
Sure.
So are you saying that f of 12 minus f of 6 is equal to AF of 12?
Yeah, right, equal. Yep.
Okay.
Do you see why? I mean, the key thing is you recognize why. So it's the exact net variation in f as x varies from 6 to 12. So that's like all those practice problems you did in recitation and for your written homework for Friday. That's a question of that. This is two different ways of expressing the same thing. Does it make sense?
Yeah, I think so. Yeah.
It's just, this is expressing as the sum of little changes, each little change calculated using the rate. This is calculating it as the final value of the quantity minus the initial value of the quantity. Gives you amount of variation. Relating that back to all that, the homework and the recitation activities you've been doing.
Mark, are you recording?
I am recording, thank you. Yeah, I'm not using Zoom to record anymore. I'm just using some screen recording software. But yes, we're rolling.
I have a question about m. So, once it's in integral form,
Yeah.
Is the integral of m, is that the rate of change, or is m itself? So is w squared minus 7 the rate of change?
Yeah.
Or
So
is
I was just
cubed over 3.
So this is representing m dx. The rate of change in this case is w squared minus 7. Generically, we said the rate was m because when we were saying dy equals m dx, right? So our whole thing was that dy equals m dx, right? And remember, we were accumulating changes, right? We're summing up these. Well, that's what this is, right? So this is the m, and then this is the dx. Does that answer it?
Kinda. So it's just the rate is still the same, but the integral just means that we're now adding everything.
Integral means adding up a bunch of these, adding up a bunch of mdx's, like we did all last week, getting up to integral. We kept saying we're just gonna. That's what accumulation is a running total, right? A running total of changes. We did that with a table, and then we did it in the function formula. Remember, we did the sum of Rx delta x, right? It's a running total summing up plus one more R dx. And then we did that in the table, so yeah.
Yeah, okay, that makes sense.
Yep.
Sorry, the integral, just solving it was throwing me off.
So we haven't solved any integrals. We're just representing what they mean. So we haven't solved any integral. But then, so I said, okay, if this integral has this meaning, well then we also know this has this meaning, right? We didn't solve anything. We just came up with a different way of expressing that using the function f. Does that make sense?
Yeah, that makes sense.
Okay,
Thank
cool.
you.
All right.
Sorry, I was just wondering.
Yeah.
Would that be f of 12 minus f of 6? Would that be the same thing as af of 12 minus af of 6?
Well,
Is that not?
It's the same value, but so AF, yes, it is. So, but AF of 12 is this, right? What is AF of 6?
Just 0.
0, right? So this is equal to 0 because it's the net change.
Thank you.
Yeah, does that make sense?
Yes, thank you.
Yeah, but neither of these are 0, right? These are both amounts of the function.
Right.
Yeah.
Yes.
Okay, very good.
That's fucking your life up, brother.
Hey, Blue. Hey, Blue, your microphone is on. Okay, here we go. So here's a practice. When Katie unties a partially filled balloon, she inflates it with more air. The volume increases at a rate of 2 over x plus 1 inches cubed per second. where x is the time elapsed since Katie began inflating the balloon. If the volume of air in the balloon is 18 inches cubed at x equals 3 seconds, write a function Vx, V of x, the volume of air in the balloon at x seconds. So could you take what we've learned and write a volume accumulation function? So what is the volume accumulation function for this scenario? So first of all, is this sorry. Is this total or net accumulation when we're talking about V of x?
Total accumulation.
Or he wants total. The rest of you agree with that? So what is our template or our basic form for total accumulation? Well, it's going to be all the accumulation up to a given point plus what? What's this going to be here?
Integral from 3 to x.
Good. So it's going to be it's going to be our net accumulation starting from 3, right? Starting from 3. And then what goes here?
Rate.
The rate of change. Now we got to be careful. We don't want to use x here, right? Because we need a new symbol that means all the x values from 3 to x. So often we use t. So there's the rate of change. Then m dx, right? Rate times change, rate times change. And then what's going to go here?
V of 3.
V of 3. Excellent. And we actually know what V of 3 is, so I could also write, what is V of 3? 18. So either way, both are valid. V of 3 plus the integral of 3 to x times the rate dt, or 18. We know that is 18 plus the integral from 3 to x times the of the rate times dt. Okay, does that make sense? Okay, then in terms of finding volumes, so in this class we haven't talked about, getting a solvable expression. This is called an open form expression. It doesn't really lend itself to solving. It doesn't really lend itself to plugging in a value, say v of 4.5, and just cranking out a number. This is more expressing kind of the meaning of what's going on. We have a starting value plus the accumulated changes of the quantity starting from 3 up until x. So what we can do then is we can put this in GC and let GC give us a number, say v of 4.5, rather than having an algebraic approach. At this point, we don't really have an algebraic approach that we've talked about in this class. Okay, so control, I'm not going to get GC out and do it, but Control Shift I will give you the integral symbol. So you can define a function, use Control 9 to define the function, equals 18 plus, and then do Control Shift I, will get you the integral symbol, and then just fill in the blanks, 3 to x, and then put your rate dt, and then come on a new line, and just do v of 4.5, and it'll tell you what the value is. It'll tell you how much volume of air is in the balloon at 4.5 seconds if this is the rate of change. Okay, any questions on this?
How did you know which function to use?
I'm not sure what you mean. Here?
Yes, if between total or net.
Oh, so it's asking, what is this asking for? Is this asking for an amount of change, or is this asking for a total accumulation? That's really the question. And like from the question, is it asking for an amount like since the starting point, or is it just asking for the total air in the balloon?
Asking for total air in the balloon.
Yeah. So because of what the question is asked, that determined that we said, oh, we want the total accumulation. So we're going to have a starting amount, even though that's after 0, we still have the starting amount at 3, and then all the accumulated changes after 3.
Okay, thank you.
Yeah, sure. Other questions? Okay, so that's an example of that. So I think now having a little practice with integral expressions, you're ready to do all the iMath AS. And of course, get the support you need. If there's a question that doesn't seem familiar, you're not sure, that's what office hours are for. You can email us questions. Please, please reach out to us if you have questions. Okay, so just quickly again, and then we'll take this to the next step here. So the review of the key functions, we've got the exact total accumulation, exact net accumulation, and we know that in order to write those in a particular context, a particular problem, what do we need? We need the rate of change function. This is a huge point. If you have the rate of change, we can write accumulation. You know how fast a quantity is changing at every moment, right? You know that. You want to know how much of it you have, and that's these functions, how much of it you have. So therefore, question, if we want to write an area accumulation function, what do we need? Thank you. Excellent. Hopefully lots of you are thinking that. You need the rate of change of area. If you have the rate of change of area, then boom, you just put it here. If you want exact total accumulation, you put it here. If you want some net accumulation of area, you just fill in that rate of change right there. And then these functions give you whatever accumulation you're looking for. So if we're going to start talking about area, then what we need to find is what is the rate of change of area? Right, and so the situation we're talking about is if you have a function and the area that we're interested in is the area of the region between the function and the x-axis. Okay, so this black line is representing my function f, and so then the blue region is this area that we're interested in. So what is we want an accumulation of area function. And so then what do we need? We need the rate of change of area. So we're going to start with the simplest example, which is a constant function, right? So the constant function is a nice simple example to start with. And so here's the current value of the area for this value of x right here. What is this, 3.7 or something like that. So what we want to do is we want to think about adding or increasing x a little bit and then looking at the corresponding increase in area. So here's like a current value of x, and then we're going to let x increase an amount dx. And then when we do that, we're going to get this variation in area corresponding to that increase in x. Okay? And so if we want to we're trying to figure out what's the rate of change. What is the rate of change of area? Well, we know that's framed by this very important equation. dy equals mdx. Well, now our y is area. So we're saying, what is the rate? What is the rate, knowing that our little change in our quantity equals the rate times a little change in independent, dy equals m dx. Okay, so let's figure this out here. So we know that the D area, that's the area of the pink region, right? And then what is dx? Dx is like the base of this rectangle. And you remember that the area of a rectangle is what? Area equals base times height, right? Base times height. So if dx is the base, then what's the rate?
Height.
The height, right? So this is our area of a rectangle, right? Area equals base times height. So that means the rate has to be the height. That should make sense. Okay, so that is the rate of change. The rate of change is the height. And what is the height? Well, that is the value of the function, right? Values of the function are the y values on a graph, which is the height from the x-axis, right? Right, this is the y value on a graph is one wrong button. Okay, so we gotta pretend we still see all that blue region there. So this was our previous area, and then we increased x a little bit and got a little new amount of area in order to figure out what the rate of change was. And by the area of a rectangle formula, we saw that the rate of change is height. Well, that height, that's the y value of the graph, and that's the value of the function. So for this particular example, the rate of change of area is 3, right? 3 is the height of that graph, or in other words, it's f of x, right? It's f of x. But is it really the same? So the rate of change of area is given as what? The units of your y per units of x. But the function value would just only be the one like linear distance dimension there, inches. So the units are different, right? You don't want to do not cancel. You don't cancel units and make it inches. Then it's no longer rate of change. It's not how much the area is changing per inch of base. Now this is strictly a distance unit. So you don't want to do that. You want to maintain this because it's a rate of change value. The function value is an inches value. It's just the distance from here to here. So we said that the rate of change is the function value. Well, it's the value. We're going to take the value of the function to get the rate of change, but then we're going to note, oh, the rate of change has different units. Okay, so we're going to use the function value, but with different units to be our rate of change of area. And those units are area unit per x unit. Okay, is this making sense? So the whole thing was, if we want to rate area accumulation, go ahead.
Could you repeat what you just said for when you were trying to relate the function to back to the rate? You said, what did you just say just now?
So did you understand that the height of the height of this rectangle is the rate of change, first of all?
Yes, sir.
Yeah, and so then what is the height? The height right there is f of x. It's the value of the function. So we're going to use the value of the function to be our rate of change, because the height of the value of the function is the height, and the height we found out is the rate of change. It's m.
All right, I was looking at them independent of the rectangle, so that's where I got messed up. All right,
so you good now?
Yeah, I'm good now.
So the key is we're going to pull off the numerical value of the function, and that's going to be the rate of change of area, but that rate of change is going to have a different unit than the function. It's going to have these. It's going to have a rate of change unit, area per change in x. Okay, so we said we want to write an area accumulation function. What do we need to write area accumulation? We need the rate of change of area. And we just discovered that the rate of change of area is the value of the function. The rate of change of area is the value of the function because that's the height. That's the height of this growing region. Okay, does it make sense? So, but then the question is, so this was for a very simplistic constant function. So the question is, what about how are we going to find the rate of change of area when f is not constant? So here's a more typical kind of generic function. F is constantly changing. So how are we going to find the rate of change of area now? So we can investigate that a little bit here. So here's a region. As x increases, as x varies, we're sweeping out a region between the function and the x-axis. And so now, but actually if you zoom in on this function, it's a little bit different than you expect. This function has been delineated into lots of little constant values instead of being continually increasing. We've taken delta x intervals and made the value of the function constant in those delta x intervals. So here's zooming in even more. And so why are we doing this? Well, so we're going to leverage what we just talked about. We're going to leverage when we have a constant function, we figured out what the rate of change of area was. So here we have x varying through delta x intervals. But we've turned our continuous function f into lots of little intervals with constant values to approximate it. So about like this, right? So we're transforming. It's kind of like it's like the pretend rate function, right? So it's like a pretend f function. All these little steps are pretending to be f. Okay, so we're going to pause. So we know x is increasing through these delta x intervals. And so we're going to pause right here. We're going to pause life and ask some questions. Can I move that? Does that move? So the first question we're going to ask is the value of x fixed or varying, and what is its current value? Is the value of delta x fixed or varying? What's its current value? And is the value of dx fixed or varying? What is its current value? So this is a really good review, stuff we talked about in the first week. And then in the current interval, is the rate of change of area fixed or varying? What is its current value? So this is, I'm going to take a minute to think through these questions as a good review of stuff we did in the first week, but now applying it to specifically the quantity of area between the function f and the x-axis. So what do we think? Is the value of x fixed or varying in this kind of the broader situation here?
Varying.
Okay, what's varying? Right. Okay, so it's varying, right? X is varying. And then where I paused it, what's the current value of x?
95.
About 95.
Good, 95. All right, so our current value of x is, it's varying, but currently, where I paused it, it's 95. Okay, what about delta x? Delta x was our what? Our chosen interval width. Is that fixed or varying?
Fixed.
That's fixed. Sorry about the bar here. So actually, I'm going to move on to the next slide because that has it better here. There we go. Oh, and I'm actually showing a different x, so we're going to start over. Okay, we're going to clear all the drawings. All right, so here we go. So now we know x is varying, and now I've got a new value here. What's our current value of x?
94.
Yeah, 94. Okay, and then what about the value of delta x? Fixed or varying?
Fixed.
Fixed. And what is the current value of delta x?
2.
So actually, it's a little bit more than 2. So this is like 91.6, and this is like 93.7. So we'll say 2.1. Does everybody see that? But that's fixed, right? We chopped up our x into delta x of 2.1, and they're staying that. They're not varying. What about dx? Fixed or varying? As x varies, right? X is varying. Is dx, remember what dx was from last week?
Varying.
Yeah, so it's varying. And remember what dx was? Dx is the amount of variation so far in the current interval. It's the amount of variation so far in the current interval. So the range of dx, it starts at, in a new interval, dx starts at 0. And then it increases until it reaches what value?
X.
Yep, the maximum dx is delta x. Because when we get to the end of the interval, we start over with a new interval. So the max dx equals delta x. So at our x value of 94, what is the current, so dx is varying in the current interval. How much change do we have so far in the current interval? Someone said 0.3, right. So here's the start of the delta x interval. Dx is how much so far? So 0.3 or 0.4, something like that. Okay. All right, what about this? In the current interval, is the rate of change of area fixed or varying? So remember how we got, what was our rate of change of area? Rate of change of area, we add a constant function value. What did we come up with on the last screen that the rate of change of area was? Huge point. Like, this is like the most important thing about area. What is the rate of change of area? Height. How do we express height, right? How do we express height?
The value of the function.
Value of the function. So, like, f of, say, whatever this was. So this f of 93.7. Right? So that, kind of like the left-hand method, right? So the value of the function right there is the value of the function at 93.7, and that's going to be our value of the function in this pretend function for the whole delta x interval. Okay, and what is that? What is that rate of change? Or an estimate?
1.61.
Good. Some people are saying 1.61. Excellent. 1.61, right? The value of the function in the current interval. And so that value of the function, 1.61, is the rate of change, how much the area is growing in this current interval, or in the vicinity of this x equals 94. And and what did we say? Is that rate of change in the current interval, is that rate of change fixed or varying? Fixed. It's based on the pretend constant function right there. Pretend step function, right? The pretend function. Okay, so really important kind of, this is the machinery, right? This is the mechanism behind all this rate of change and accumulation. These questions are super important. Do all these, what we said, everything makes sense given the picture here? Or is there a question?
Just for the question number one.
Yeah.
When you said that x equals 94,
Uh-huh.
is that the same as the 93.7? Is it just kind of like
No, it's not. Actually, 93.7 is the start of the delta x interval. But I'm showing the current value of x is like how much shading we've had so far. Do you see that? So here,
Gotcha.
yeah, there's x. The 93.7 is the beginning of this current interval.
Got it.
Good question. Thank you. Good question.
Where do we see delta x within the actual integral, like the net accumulation integral?
The integral? Well, it came, so we used delta x for the approximate accumulation function. Remember, it was the sum of Rx delta x, where delta x wasn't small, and then we had plus Rx current dx. And then we said, as delta x gets really small, then we get the net accumulation function, which is the sum integral of the rate dx.
So it didn't disappear, it just got really small.
That's right. Right.
Okay, gotcha.
But when we're thinking in terms of these delta x, these large kind of not small delta x's, we just remember that, well, for all delta x's, we're thinking about dx increasing from 0 to delta x in the current interval. But then when everything gets small, we just think about dx kind of increasing continuously, right? Dx is just like these little bits that are just increasing continuously through there. Does that help?
Yeah, thank you.
Okay.
So when you say the rate of change of the area is fixed for the current interval, that just applies for the current interval.
That's right.
For the whole thing, it would be varying.
Yes, but the key is, the very key point is we're keeping it fixed in the current interval. So yeah, from interval to interval, it changes, but we always are interested in what's happening right at x. That's the most important thing, to focus on what's happening right at x. And right at x, we're assuming that that function value and the rate to stay constant. That's going to be a very important point when we get to volume. Okay, what we're interested in is what's happening right at x. Don't focus on the fact that the rate changes from interval to interval, but focus on the fact that at x, the rate is considered to stay the same. That's the most important thing. Okay, so let's just summarize that. So here's that image again. Now we know how to do this. Now we know how to get the rate of change of area. We think of that function as a zillion little constant rates, a zillion little constant values of the function. This is really a staircase for a flea, okay? So that's the way we want to imagine it. It's like the staircase for an atom or molecule. All right, so quickly, what's the current value of x here? Current value of x is 2. What's the current rate of change of area then? For this one, if the current value of x is 2, what's the current rate of change of area? In other words, the rate of change of area at 2 equals what?
F of 2.
Good, f of 2. And then we could estimate it, right? We could estimate it as approximately 2.4. That's what I'm seeing. Does that make sense? So at x equals 2, the rate of change of this blue area as it's growing is the value of the function at 2, f of 2, the height. And that's about 2.4. Over here, what's the current value of x? X is about 4.9. The rate of change of area now is at 4.9 is f of 4.9. Okay, notice it's not the rate of change of f. This is the big confusion students have. The rate of change of area is the value of the function itself. It's not the rate of change of the function. Okay, so be careful. Rate of change of area is the function itself. And that's about 3.75, or is it 4? Oh, 3.8. Any questions before the quiz?
Sorry, could you make that point again about the rate of the changing area?
Sure
or
thing.
The rate
Sure
of the
thing.
area is 4.9 is equal to f of 4.9.
There's another function. So there's also the function, the rate of change of f. The rate of change of f has nothing to do with what we're talking about. The rate of change of area, so we have an area function, right? As this thing grows. The rate of change of that area function is the height, the value of the function f that's defining the top of it. But the rate of change of the function is not involved here. Don't confuse. Don't say that the rate of change of area is the rate of change of f. No, the rate of change of area is f. It's the height. It's not the slope of the tangent curve, slope of the tangent line. It's the height f.
Gotcha.
Is that better?
Yes. Yeah. At that current x value, it's the height. Yeah.
It's the height. It's f. It's not the rate of change of f.
Yeah.
Don't use that.
And that's why we have all those little staircases, because the height is changing as f.
Right. So we think of a really small interval for which that height is the same. Right there.
Right.
It's staying constant.
Perfect.
And now we can do rate of change. So the area is going to be integral from 0 to x of, what's the rate of change of area? F. There's our area accumulation function. Okay, take the quiz. If you haven't started yet, make sure you go take it. And then remember, 2 homework assignments due Wednesday at 9 a.m. And I'll see you Wednesday. And I'll stay here for questions, as always.
Sorry, I know you just went over it.
Sure.
But the rate, the RF of x thing,
Yeah.
that's giving us the actual line versus the R area, that's giving us the area under it. So that's...
Yeah, so so we have this function that's giving us how much accumulated area we have. That's the blue. That's like the area of x. Okay, and then
and the other thing,
so I should have written area x equals. Okay. So that's what we're after. We're after a function that gives us the accumulation of this blue region. So we said, what do we need? We need the rate of change of area, right? And so then we used most of the class showing that the rate of change of that area is just this dimension right here, the height. Well, that height is f of x. That's the rate of change of area. So that's why I'm putting, here's my rate of change for my area function. 0 to x.
Okay.
Rate.
okay, got it.
Now, what I was trying to warn you about is students, instead of saying this is just the function value, because this is the rate of change of area, they want to make this the rate of change of f. It is not the rate of change of f. The rate of change of f is like the slope of this tangent line. It's how much y is increasing with respect to x. That has nothing to do with our area situation.
Okay.
Is that better?
Yeah.
So watch out.
Thank
The
you.
rate of change of area is the function value. It's not the rate of change of the function value.
Okay, cool. Thank you.
You're welcome. Other questions?